We're going to have our first panel discussion now. So thank you to this morning's speakers and Professor Warshel, Professor Saykally, if you would please join us up here on stage. And Professor Young will serve as the co-moderator today from the Young Lab here at Berkeley. So we encourage questions from all, especially the students. This is your chance. And we're also going to be taking questions from our webinar, which has been quite active this morning. So please do not hesitate to come up to the mics, and we will take as many questions as are possible. So while you have a chance, Professor Yang, would you like to start off maybe with a question?
Yeah. So maybe I can kick off this section. We heard 3 fascinating talks, and the water is indeed very strange. It's a very strange molecule. So I was very, very fascinated by Professor Zare's talk. The water droplets has amazing reactivity. Essentially, we're talking about the electric field, very, very strong electric field, and decrease the activation barrier of many reactions, right? So I was thinking while I'm listening to your talk, like on the beach side, we have all the minerals, right? Then ocean, we have all these ocean microdroplets full of minerals, sodium chloride, and certainly they are in contact with nitrogen. So I would say on the beachfront, we have big factory going on over there, lots of chemical reactions. We're producing ammonium over there.
Do I push this to make this talk, or is it,
Yeah,
is it just by itself? You hear me? It's very interesting. I think water droplets or water sprays are ubiquitous. Not only do you find them in ocean sprays, you find them in rain, you find them in geysers, you find them all over the place, okay? And I'd like to move this yet further in another direction and tell you that a number of us search for how to turn non-life into life. And if we are asking ourselves in prebiotic chemistry, how is it possible that we got such things as, for example, peptides and amines? How do we get bases? I want to point to the ability of water droplets. I only emphasize to you the electric field, but that's incomplete. There's several other things that are going on. Really, solutes, many of them want to collect at the interface, if you look at the partitioning. Number 1. Number 2, it turns out that you don't have 3-dimensional hydrogen bonding anymore. Well, you can't by definition. It's the interface. And the result of that is that the reactivity greatly changes. Another fact. Third fact, there's this electric field, but it causes something else to happen. Many molecules are polar, have a dipole moment. They're going to align at the interface. We've seen this with polarization experiments. Once we've aligned them, we're going to change this, what do you call it, stereodynamics of what can all happen. Oh, there's so many possibilities here, and I'm not sure I've named them all yet, but you get some idea. Evaporation, concentration further. I don't want to leave all this out, but wow, there's so much here. Okay, so yes.
So you believe actually eventually this sort of maybe one can make even amino acid using microdroplets.
Or you can, from amino acids, already I saw some lovely work done first by Veronica Vida and then later by Graham Cook's group, in which they've now made peptides, dipeptides from amines in droplets. You can't get them in water. It turns out, I forgot to mention again, delta G is positive. Dipeptides will actually hydrolyze, come apart into amino acids in pure water. But at the interface, they form. Okay? And
Professor Warshel, do you have something you'd like to add to that?
No, I mean, in some of our early simple dipole model, we found out, this is 1979, that if we don't have the bulk boundary condition around the droplet, the energetics is very different. So I completely, whether life started in droplet or by aliens, I was not there.
I was not there either.
So let's take the question at the microphone, please.
Yeah, it's more a question or a comment regarding the discussion already going on. Do you think that reactions happening at the droplet surface could be also explanation for why we have basically enantiomer selectivity in our amino acids in all living forms? Because you have kind of not the 3-dimension, but you're restricted in the dimensionality, and that is... I was always wondering why we just have one enantiomer in amino acids.
She asked if we have only 24 amino acids because in droplet. It's a nice paper for Nature if you.
I'm sorry, you say for Nature, I'm rather down on those matters. I'm telling you, if it's too new, it won't be accepted by Nature.
We know.
Okay, I'm serious. And what I'm trying to tell you.
If it's very speculative, it might be accepted.
Depends how it's couched, that's right.
Could we have the next question, please? And if you don't mind identifying yourself and where you're from.
Well, I'm from Nigel Richards. I'm hanging out in Berkeley. So I don't understand a couple of things. The first thing is I don't understand where the oxygen goes to in the reduction of nitrogen by water. I assume you're making molecular oxygen. And if that's true, if you leave the nitrogen out, shouldn't you just be splitting water to O2 plus H2 in your system?
I think it's quite possible that the oxygen is ending up in part in HOOH, hydrogen peroxide.
I see. Okay. But is that... Well, okay. And then the second question is I don't understand where the energy is coming from. So I understand it costs you a certain amount of energy to turn nitrogen into ammonia, but in your system, where is that coming from?
I believe it actually costs you energy to make water droplets. You have to take water apart to make the water droplets, I didn't show you. I have slides which show this. You need little water droplets, not big water droplets. It doesn't work for big water droplets. It works for little water droplets. On the order, best is around 1 to 10 microns. A human hair in diameter is about 100 microns. So about 1/10 of a human hair to 100th of a human hair is really good. Okay. And I need to say something else which is maybe surprising. There is a very important matter of a double layer, electric double layer. And if your water becomes a cluster, if it becomes too small, the effect again goes away because the double layers overlap. So this is something that's I know this is going to be frustrating. This is not nanochemistry. This is, what do you call it, mesochemistry or microchemistry, something like that. It's what we're talking about. And it's really different.
If we can take the question over there.
Yeah, so my name is Calton. I'm a student here at UC Berkeley. But I have two questions for Professor Zare. One is for just the nitrogen and water system, do you know what the chemical potential of the electron is? Like, what is the driving, like, how much driving force is there electrochemically?
Yes, I do. I have that actually published. It takes you easily high voltage, depends on pH, to remove OH minus to make OH plus an electron. But it on the order of like 1 electron volt or more. But it turns out you have that energy at the interface with your electric field and with fluctuations in your electric field.
Okay. And my second question is regarding the CO2, nitrogen, and water system. I saw in the diagram you use an electrospray ionizer in the beginning. Doesn't that create so many excited species that those excited species could be the one doing the chemistry?
No, because I can turn it off. Without the catalyst, I get nothing. Again, I don't get anything like what I'm showing you. I need the whole system to come together. But I understand your question, and it's a good one. But no, it's not just being done by my driving it with electricity input to make a droplet.
Oh, I meant like, let's just say instead of using electrospray ionizer, you just use an atom, like a spray coater.
Yeah, I can do that. It works just without any electrical current being applied from anywhere. It really does.
Okay.
Before we take the next question, here's one for Professor Saykally. What makes water wet?
What makes water wet?
First, I need to know who asks that question.
This came via our internet, so we're not sure.
If this is coming from students,
You can assume it's from a student, yes.
okay, then I used to run a middle school outreach program at Berkeley for quite a long time. And in the course of that, we got some very interesting answers. So what would you say, well, when I would show this stuff to my colleagues in a physical chemistry seminar at Berkeley, for example, ask them, what do you think makes water wet? The sophisticated physical chemists and the theoreticians would say, well, Saykally, first thing you got to do is define precisely what you mean by wet. And I had a very good answer for them. I had a big squirt gun, and I would take it over to them and squirt them with it. That worked. But the academic answer is, what you mean by wet really are all these properties of water that are extreme. Water has extreme properties relative to other simple liquids. The cohesive energy is very high. The boiling point is very high. There are all sorts of these properties of water that are very unusual. And those properties are what we mean by wet, okay? So then the question would become, what is responsible for water having all these these extreme properties? And the answer to that is strong tetrahedral hydrogen bonding. That's what gives rise to this. So water forms these very strong hydrogen bonds, and it wants to make 4 of them. 2 where the hydrogens donate 2 hydrogen bonds to a receiver, and the oxygen accepts 2. So it's those strong tetrahedral hydrogen bonding networks that make water wet.
May I add something to this, if I might? Okay. I'm going to tell you for fun that at the interface, often, the water in some sense is dry as opposed to wet. More water slips by water, and it's much more wet in the tetrahedral. But at the interface, it gets dry. And we have seen measurements in which it's clear that the viscosity of water changes at the interface.
But if we spray you with water, you will not be
Yeah,
dry.
But I'll go on now further about this interface effect. We all are here in California. California is famous for its redwood trees. Redwood trees easily go, 80 meters into the air, something like this. If you try to pump water, how high can you pump water? 10 meters, right? And that's indeed I'm trying to think of his name. Was it Torricelli in the water barometers? Why we use mercury for a barometer instead of water? You don't have to go 10 meters. Okay, well, how is it possible then that water can go to the top of a redwood tree? And it does. And what you have is you have their capillaries, and you have the water, cellulose, wood interactions, and you can actually then pump water much higher. In skyscrapers, okay, you really need to have pumping stations, and they do, to bring the water up, but not for a redwood tree. It has its own built-in pumping station through this effect that I'm telling you about at the interface.
If I can add a little bit to that, first of all, the explanation of what makes water wet does not apply to the interface at all. The interface is a completely different beast as we are learning. There's a new language that we all need to learn to describe the interface. It's called, from David Chandler, as I mentioned in my talk, the instantaneous interface. It's a layered system where the waters have different orientation and different bonding patterns in the different layers. It's very different and undoubtedly underlies some of these properties. One more property of water droplets that we ran into a long time ago that I find very interesting, very much like what Professor Zare talks about. If you squirt water through a capillary, through a narrow tube, and first the water emerges from the tube as a stream of droplets by Rayleigh effect, as it's called. But you get this droplet stream emerging from the capillary, and those droplets turn out to be very highly positively charged. And we had to figure out what was going on there because we used those jets in our X-ray experiments, and we found that we could make the charges go away on the droplets if we just took a salt shaker and put a little bit of salt in the water that we were spraying. It destroyed the charging. But another good thing is we put a metal target downstream of these positively charged droplets that were emerging from a capillary, and it generated hydrogen. So we have a patent on this electrokinetic hydrogen generation that I hope somebody buys, because the only energy source you need is water pressure. So, but that's another strange phenomenon that fits into this water droplet thing.
Okay, thank you. We have somebody patiently waiting for a question.
My name is Ali. I'm a PhD candidate from Yagi's lab. I had two questions. The first question is, have you investigated the nebulizer system with gases like carbon monoxide? I don't know, I just thought about what if you can reduce carbon monoxide into...
I try very hard to keep carbon monoxide out of my lab. Or if in my lab, at least inside a cylinder. No, I have not done carbon monoxide as a nebulizing gas. Sorry, there's many more things to do here. This is so much in its infancy. You can play with other things. We're starting to play with things and finding many phenomena. We've used toluene in water. And toluene has no great solubility like benzene in water, very bad. But we can, again, make all types of reactivity occur. If we add toluene's this benzene ring with a CH3 on it, just so everybody knows. We find that if you just spray toluene in water, okay, we get what's called the benzyl radical, a CH2. The hydrogen comes off. Again, quite interesting chemistry. All types of things are possible to be done. Now the question is, in my mind still, whether this can be brought to a level where it's preparative as opposed to, oh, a gee whiz in the laboratory.
If you may allow me, I have a second question. So for this phenomenon I've been really happy with the presentations given today. Can you observe this in other systems? I thought about, let's say, a thin film of water. Would you also see the same phenomenon observed over there?
Yes. There's a quick first answer. Next thing is, if you replace the water with an organic solvent like pure methanol or pure acetone or pure acetonitrile, CH3CN, no effect. You need the nature of water with its ions being formed. I do not know about ionic liquids. I wish I could investigate that some. That's more to be done. I know that if you'll mix some water into acetonitrile, you can turn the effect back on. Okay, there are other things here. Much to be done.
Thank you.
Yes, go ahead.
Hello, my name is Yao. I'm a middle fellow working with Peidong. Question may go to both Richard. So my question actually is about, do you have a sense of the concentration of hydroxide radical in the water? How long do they survive? Yeah, I guess.
wants to know about the concentration of hydroxide radicals.
Yeah.
I know that they don't survive. They go on and do something. They either get complexed by water itself or they go find each other. And when they find each other, they form HOOH, and we call that hydrogen peroxide. And provided you don't have strong visible light or UV light, that survives for months in water. As you know, you can buy it in the store.
I see. So do we have a way to measure the concentration?
Yes.
I see. Yes, kind of the reason I ask, what may concern our research is...
And I was trying to show you that we can actually calibrate, for example, with nuclear magnetic resonance and measure it as an ice way. And there are other techniques.
I see. I also want to kind of get your comments now. Our research actually involved we shoot high energy electron X-ray beam into the liquid to try to observe how catalysts evolve. Quite often we keep the beam dose way below the threshold to minimize the concentration of radical. That's why I asked the question, do we have a way to probe the concentration but not damaging the liquid?
Often you can add some compound that will react with a radical and become itself, change its spectroscopy. And you can see that spectroscopy in a number of different ways. By absorption, by fluorescence, or by electron spin resonance, or by NMR, various ways. Okay? So there are ways.
Okay, thanks.
Okay. Go ahead.
Yeah, I have two questions. Dick, for your system, you use a catalyst when you form ammonia. Are the yields dependent on the catalyst you use?
Yes.
And the chemical nature of the catalyst? And you said something about nitrogen binding, being absorbed.
Right.
But these catalysts may be doing something else as well. And the contaminants in the catalyst, I mean, I could go on and on, but just that's the general question.
I wish I
anyway.
knew the answers to what you were asking.
Yeah.
Because I remember in the Haber-Bosch process, they're still arguing about whether contaminants play what role and how the process happens, as I recall. So these are very good questions, and there's much more to be done here. But I know if you change, if you were to just use plastic or Teflon, you don't get ammonia. No way. Nothing happens.
But you have one catalyst in particular that seems to be
Well,
the
we
most
picked
effective?
the
iron
one
oxide?
that the Haber-Bosch process is famous for, right? And why did we pick copper oxide and bismuth oxide? Is it because I'm some genius or personally, in inorganic chemistry? No way, sorry. It's because I looked at the literature and saw what people were doing in electrochemistry and copied them,
Right.
what they'd already found.
I
There
have
may
a
be better catalysts. That's to be found out, okay?
Yeah, very, very fantastic. Arieh, I have another question for you, if I may. It has to do with forcing water into the interior of a protein. Because proteins, enzymes in general, are thermally activated. The water is the heat bath. And so the question is it just collision of water with the external surface of the protein, the loops perhaps, or is there actual water permeation that could be driven by the collisions? And whether you've looked at that or thought about it in terms of the dynamical activation of proteins.
First, I strongly believe in energetics. So the question is, at the given temperature, what is the chance or the free energy of water to be at a given site? It has nothing to do with kinetic energy because it's being dissipated. So it's a question.
Well, there's energy transfer going on.
You're
You're activating the protein.
There is
yeah.
thermal, there is a detailed balance, and there are water around the protein, and the chance that a given water will be at a given site in the protein is given by the free energy. So this is after, I mean, we don't consider the barrier for penetration, though it's also a good question. But what is the chance with a microscopic reversibility to be at a given site?
Protein is breathing all the time on the surface, local unfoldings going on all
Everything
the
is,
time.
you want my response to dynamics, which I don't like.
I know.
Everything is moving all the time. And at the end of the day, if you have microscopic reversibility, if it's not result of sudden heating, this would be my question. When I want to know what is the chance of an enzyme to react, and I want to know how many water molecules are in contact with the place where there will be the transition state, this what I would
Yes.
try to model.
Yes, that's what we'd like to know, sure.
I'd like to add a little to it about interface, if I might. The term free energy change, we call it delta G. It's really equal to two other terms, or delta H minus T delta S, okay? We teach that type of stuff, right? Well, delta H is very much an energetic type thing, but your entropy change is very different at the interface than it is in the bulk. And we've done experiments as a function of temperature to find that. And we find that things again become much more ordered at the interface, and that your entropy has been reduced, and it can change the sign of delta G just by this
Sure.
process.
Yeah, well, this is a long question, but I just wanted to focus on what you were talking about in your modeling, which was the permeation of the protein in the computer. You can do that, the permeation of the protein by water. And of course, you were looking at pKa's, but there may be other effects going on there in terms of the catalytic
For
process.
drug binding,
Yeah.
this is crucial. For cytochrome C oxidase, you want to know how much water are around different proton acceptors, because this determines the energetics.
Sure. Yeah. Thank you. That's great.
I wanted to add something more about enzymes, because we looked at some of the enzymatic reactions of, for example, the digestion of proteins by trypsin. And we find that they're hugely accelerated in water droplets compared to bulk water. In bulk water, often one has to run the experiment overnight to make the digestion. We find we're able to actually succeed in getting even more digestion in a millisecond if it's made into water droplets that contain trypsin.
I have to think about that. That's a really interesting observation. Thank you.
Thank you, Professor Gray.
Hi, my name is Harry Gray. You'll hear more from me later, but right now I want to know from the three brilliant people we have up there, what's your definition of a water droplet in terms of the minimum number of water molecules where the conversion goes from a water droplet to a bulk water? What is that number? Rick, what is that number for you?
I know for me that if I'm at the size,
Rick.
I want to answer.
I figured you're going to answer, Dick.
Okay. If you are 100 microns or larger, it's acting pretty much like bulk water.
Okay.
If you are less than that, it starts to act like a water droplet. I don't know how small you get where that turns off, but I think it will.
But that's
turn off.
still a lot of water molecules.
That's correct. This is very much.
Because Avogadro's number
That's
is pretty
just
big.
somewhere where like 1 or 0.5 to 10 microns
Yeah.
in diameter.
Is that okay with you guys, Arieh and Rick?
I mean, here is the expert.
I would simply say you need enough water molecules to have a bulk and an interface
Yeah. Yeah.
So that's going to be
Yeah, that-
in the
I
1
would agree with that.
micron or 100 nanometer region.
And a question to Dick. You know, Dick, there's an enormous number of papers in the literature on electrocatalytic production of ammonia from dinitrogen, allegedly. But most of them are wrong because they haven't done the proper controls. And I assume you've done all the proper controls, that you've shown that N15 nitrogen goes to N15 ammonia.
Well, I haven't done the N15. I've done some of the controls and believe that what I'm telling you is so. Okay, I'll have to give you a copy of the paper for you to decide.
Okay, will do. Thank you, Dick.
Thank you. Over here?
Hello, my name is Rachel Kimball. I'm a junior currently at Crondalette High School, and you mentioned there was an energy change at the interface, or an entropy change, sorry. I just want to ask why. What makes it an entropy change?
Well, first of all, let's make sure we understand entropy. Entropy refers to randomness, random orientation, the rest. And I'm telling you that things become ordered and they become more rigid at the interface. Now you see the change, I hope, okay?
Thank you. Although, why does that happen? Why does it become more rigid at the interface?
Because we have a very strong electric field that's going to work on the dipole moments. You just showed us what the dipole moment was, the water itself, like 1.8 something, and it's going to act on it.
There are less ways to orient the water on the interface. Instead of being in the bulk where you have, I will count 4, but there are different ways to satisfy the structure of water. On the surface, you have to point out.
So we've watched molecules that can undergo internal rotation and therefore change their fluorescence lifetime. And we find at the interface that's turned off. They become rigid. I have publication I could share with you on that and show you that really we do know this.
Thank you.
Professor Norden, you're next, and then we'll go over
question. Dick, what makes your interface so magic? Is it how its proportion compared to the bulk, or is it the curvature of your microdroplet?
I wish I understood it all. I've done some calculations, and certainly it depends on size. It does, and that certainly can be related to curvature, but I'm not sure I fully understand. There's gradients being set up in the water droplet itself. It's not simply just at the interface. But maybe Professor Saykally want to add something to that. I don't know. No. Okay. More to learn. Okay.
Go ahead, please.
Walt Yang, Cal. So I had 2 questions. One would be for Rich. Well, first of all, thank you for playing the guitar and not singing. And I was just wondering, so you were talking about the Gibbs dividing surface and how it's sort of outdated. And you had some experiments looking at, probing the interface, SHG looking at really the monolayer, like really something that's the surface, and then your XPS looking at nanometers deep. So I'm wondering if through these 2 experiments or something within your career, is there like a big difference between something that may be defined as truly the interface, as in a couple monolayers or some salvation shells, versus something that can be more smeared, as in like these nanometers length scales?
Yeah, as I said in my talk, traditionally the interface of water is defined by the Gibbs dividing surface, which is the halfway point of where the density drops roughly to half of its bulk value. That's very deep. And most of these phenomena that we're discussing happen in the outermost layer or the outermost 2 or 3 layers. It's very different. And like I have said, there's a new language that has been developed to address this. It's called the instantaneous interface by Willard and Chandler. And their modeling shows that the interface of water is layered. There are 3 or 4 layers that have different orientations of the waters in those layers. There's spacing between the layers, and then it goes to the bulk sort of configuration. And therefore, once you start digesting this new language, it's not surprising that you get so many surprising results, like we're hearing from Professor Zare and so on, when you do interfacial studies. It depends how deep your particular process probes into that layered structure.
And I guess a quick follow-up for that is that, so I think you mentioned in your XPS that you can actually change the energetics to probe different depths, I would say. So I'm wondering, is there experimental techniques that you can actually probe these individual monolayers very selectively? I'm not sure if there are any currently.
Nonlinear optics can do that to some degree, but there hasn't been a technique that can systematically probe the outermost layer, then change it to go to the next layer and the next. Typically, nonlinear optics probes the outermost layer or perhaps the outermost 2 layers.
Okay.
So it's very different than XPS, which probes 5 nanometers or something like that.
There's another scary aspect, at least scary to me. You get fluctuations so that the layers are not just simply static.
True. And then my other question was for Professor Warshel. So I was wondering, I was really intrigued by your water flooding kind of method, and then how you validated it through your Monte Carlo simulation many years later, due to sort of the advent of better computational skill, or like computing resources, I would say. And in my view, at least from what I understood, it seemed like your water flooding sort of procedure was like biasing the system very heavily. And because you were looking at trying to discover rare events. So traditionally, I would be thinking about things like transition path sampling or umbrella sampling, where you have to be very careful about biasing. So I'm wondering if that was just a situation where you biased properly and were able to sample properly, and if there's any breakdown of this water flooding procedure.
Okay, so first, I don't like transition path sampling or anything which work with infinite attempts. We could go from the end, from the 1918 paper, where we did grand canonical, and it appears that, and you could validate it first by number of waters that you find in different sites of protein where you know how many water you have, and sometimes by the resulting pKa, or how much it improved binding energy. Now, this approach, you balance it, the macrocanonical is biased, and you check the bias by changing it, by doing longer time and so on. So the grand canonical is it's similar to umbrella sampling in the philosophy, and the water flooding is validated by reproducing the result of the grand canonical. Now, first, as all of my approach, it was intuitive, but then eventually you validate it by something. So since it gives results similar to the grand canonical, and by the way, there is not much biasing there. What we do, we build a grid of possible water points where the cutoff of protein is smaller than usually. So we have a lot of water in the protein. Then we relax it, some water escape, and then we calculate by linear response approximation what is the approximate free energy of each water. And then the rest of the sampling is done by these numbers. So you try to generate different water configurations only in the sampling approach, not in the penetration. I don't think it's bias. And again, you could validate it by the number of water in different sites, which this 1918 paper does.
Okay, I see. So it's more like you have the intuition for the actual methods, and it's sort of like, I
I
guess
al-
you validate through these nuances in the intuition.
You always validate few years later.
Okay, sure. Thank you.
Thank you. Please.
So I have a question for Professor Saykally. You showed tetramer have two local minima, while trimer had around 20, dimer has 8, water tetramer. In one of the slides, the water tetramer had 2 local minima only, while the water dimer had 8, trimer had around 20. What is the reason that it only have 2 local minima? Can you get me?
I couldn't understand. Wants to minimum
Do you mind
trimers and dimers.
repeating the question?
Yeah. So this is regarding the number of local minima. This is regarding the number of local minima.
Your question is regarding water clusters. How many minima are there in the potential energy surface?
Yes, so why the tetramer has only 2? The tetramer water you showed it has 2 local minima, while trimer had around 20, dimer had around 8. I'm just curious why this tetramer...
Trimer has 96 minima in the ground electronic potential surface. Those are produced by the vibrational degrees of freedom. So trimer has 96 identical minima, and the system can quantum mechanically tunnel among those in a fashion governed by group theory, and we go on from there. The dimer has 6 identical minima for the dimer, but if you allow, well, that good enough. We'll let it there.
No, but for tetramer it was 2. If I remember correctly in the slide, you said tetramer have only 2 local minima. Am I right?
He says that the tetramer, according to your slide, has only 2 minima.
No, that's definitely not true.
Oh.
You can't just look at the structure of it. You have to work out permutation group theory for this to see how many. You change the numbering of the various atoms and use permutation group theory, and that's what tells you how many identical minima you have on the ground potential surface.
Okay. So next question is regarding the bicarbonate on the water interface. And you said they were stabilized by counter anion, sodium chloride and all those, right? What is the source of sodium chloride in a pure water? In your reaction, where did the sodium chloride came from?
I can't. I'm very hard of hearing. From my years playing in a rock and roll band, I can't hear out of this ear. So sorry.
So I was curious, where does this counter anion sodium chloride, which stabilizes the bicarbonate on interface, came from? The source of sodium chloride.
Chlorine. Where's the chlorine? Counter.
Chloride.
Chloride.
These are results that are coming from the simulations of Todd Pascal, correct? And the idea is that the multiply charged ion, namely carbonate, attracts whatever positive ion is around, which turns out to be sodium and protons. So chloride is not active in that complex. So what Todd shows in his simulations is that this so-called agglomeration phenomenon turns a multiply charged ion into a quasi-neutral species, which is why it can exist in high abundance at the interface. So you got to stay tuned. He's not finished with these simulations yet, but the chloride ion doesn't play an immediate or profound role in that.
Experimentally, it comes from the fact that the water's generally in a container. And the container.
That's what I was curious where it is coming from.
Before I go to the next question, we have a question from the internet, and that relates to you, Professor Zare, where you spoke about that humidity and moisture can lead to virus control. Could you expound a bit on that?
Thank you for this opportunity. I'll remind you, when the coronavirus pandemic first started, we were told repeatedly that we should wash our hands, wash all our groceries, wash all the surfaces, and washing is great, but it has very little to do with the spread of these airborne infections. We know now it's through droplets, not by coughing or sneezing alone, but even by speaking, or worse still, by singing. We know this. Okay, so it's airborne and it's in droplets. Now, I just showed you a picture in which droplets themselves, if they're a certain size, make hydrogen peroxide, make reactive oxygen species. I have data from my lab which shows that that's guess what? A viruside, a bactericide. It kills things. Okay? So here's the question. How long will the droplet hang around? If you have very low relative humidity, the droplet quickly evaporates. The virus is very happy to be in a desiccated state, often covered with carbohydrate, vitrified in some way. It floats around for a long time in a small state, goes into someone's healthy who breathes it in and gets sick. Okay? If you are in a higher relative humidity, then the droplets have time for the reactive oxygen species to kill the viruses. This is very, and we have...
Do you have any epidemical evidence for it?
I think what I'm giving you is an explanation for why there's seasonality to viral infections. We all talk about a flu season, but they never talk about why it's so. And I'm explaining it to you. In the wintertime, we heat the air to keep ourselves warm, and we all live in houses or buildings, and you spend about 80 to 90% of our time in these enclosed structures, okay? And that dries out the air, and it's not good for us. Now, I'll tell you the worst situation you can have is the overventilated airplane. They brag about how often they change the air over in an airplane. Anybody who's taken a long air trip, and I just came from Washington, D.C., knows that they pass out water because you get dehydrated because the relative humidity in an airplane is around 5%. Awful, okay? And that's not what you want. If you can get to a relative humidity somewhere around 40% or so, it's really good. It kills things, and it's what it is right. And so it is not that I'm against ventilation. I'm against ventilation which doesn't also take into account that you want to hold the relative humidity of the indoor air at a good level for you. I hope that gives you an answer.
Thank you. Go ahead here, please.
Hi, yeah, this is for Professor Zare. So you said that there's no voltage or extra outside energy involved in making urea with your process. Where you said earlier that that energy is coming from the splitting of water droplets, right?
And again, in spraying it, that's right, making them come together. That's right.
Yes. How much energy would be in a single molecule of water then, since it's not bound to any other hydrogen bonds?
Let me think about that and get an answer. You email me and I'll give you back an answer, okay? I can't do it on the spot here.
Few hydrogen bonds. What do you mean energy in a single water molecule?
Basically, you need to break 2 OH bond.
180 kcal per mole.
Yeah, this is a very good
breaking bonds or breaking the...
Yeah, very good question. I actually have a similar question. Rich, you talk about you have this jet to produce hydrogen, right? You talk about this as the jet of water producing hydrogen,
Yes.
right? Same thing, what is the energy input over there? In both cases, you build up your electric field, but somewhere energy has to come into your system. Is that the energy you put in to make droplets? That's enough? That energy is enough to do the follow-up reaction?
The reaction are thermally activated. The whole concept is problematic. You have activation barrier, and you have a temperature of the experiment. This determines everything, and especially if it is exothermic.
Yeah.
So you don't need energy from anywhere it's the irreversibility of the process which drive you. You don't stand there and break bonds by some energy from the outside.
Xiguan, a question from you.
We just heard two breakthrough technology today, and I didn't anticipate. One is Zare's use water droplet synthesis ammonia and urea. But I want to know can you control the water particles, the size? Can you precisely control how many nanometers?
We use light scattering to actually make the measurement, so that's how we know something about the size. And how we control the size is we control how big the capillary is and what the flow rate is. So that's how we're actually making control of the size.
For industrial scale.
Now,
you needed to
here I don't yet know the answer, but there are things called fog machines, mist makers. I need really engineering help to make this, to go. And this is just the beginning. It's not over in any way. I don't have an answer to you yet.
Professor Saykally made an off remark, not in his slide. He said can produce hydrogen from water through some kind of methodology. You even asked somebody with license patent. Can you explain to us what methodology you can generate hydrogen from water without electrical license?
Our system that produces hydrogen is actually quite simple to understand. I don't think there's too much esoteric stuff there. So first of all, if we have a capillary, it's let's say a 1 micron diameter capillary, and if you pressurize water and squirt it through that capillary, Rayleigh instabilities, which are essentially sound waves, will, as the water emerges from the end of the capillary, these sound waves get amplified, and that turns out to produce a bunch of droplets. So the energy for that process is coming from the driving pressure of the water. So you make this beam of droplets, but the question then is, why are they positively charged? In our model it's the interaction of the water, even before it forms a droplet, with the surface of the glass. And it turns out that the hydroxide, in our model, the hydroxide ions are attracted toward the surface, and that leaves the positive hydrated protons behind. So when you spray out the end, the water droplets are dominated. They have more hydrated protons than they do hydroxide, and the surface of the glass in this case is conducting the negative charges in the other direction.
I agree. We've seen this.
Yes.
Yeah, and this, we call it contact electrification.
Well, hope someone can industrialize this. Need a lot of engineers.
Sorry, I couldn't hear you.
Industrialize.
Well,
Company can industrialize.
We have a patent, and I would be thrilled if somebody bought it. We can negotiate.
Great. World-changing ideas.
But to finish the discussion, the way it makes hydrogen is these positively charged droplets, we impinge them on a grounded metal electrode. So electrons flow into the metal and they neutralize the protons in the water, and it makes hydrogen. That's pretty simple for us. We don't have very esoteric explanations for that.
Okay, we have a few more minutes before we invite you to a very nice lunch. I would encourage any of the high school students who still have questions to perhaps ask now. This is your chance to ask a question one-on-one to one of our esteemed scientists here. And if there is no further questions, Professor Yang, do you have anything else you'd like to add?
Yeah, I don't have anything else to add. I think we had a lovely discussion. Enjoy the whole program.
Thank you so much. And this afternoon, we have a very exciting program for you. We have Nobel laureate Frances Arnold and Professor Whitton Stafford, who will speak to you this afternoon on some very exciting topics. So please enjoy your lunch and be back here by 1:40, and we will resume. So thank you all, and appreciate your time and also that of the speakers.